Hello students, welcome to MJ's chemistry classes. This is my second video on solid state chemistry. In this video, I will be discussing about elements of symmetry, laws of crystallography, Weiss and Miller indices. First, let us know what are the elements of symmetry. There are three symmetry elements. First one is axis of symmetry. There are four types of axis of symmetry with respect to crystallography: two-fold, three-fold, four-fold and six-fold. Second one is plane of symmetry. It can be of two types, rectangular and diagonal. Third symmetry element is center of symmetry. There can be only one center of symmetry possible. Now let us discuss about axis of symmetry. It is defined as the imaginary line passing through the crystal such that when the crystal is rotated about this line, exactly similar appearance occurs more than once in one complete revolution, that is, in a rotation through 360 degree. Let us know what is two-fold axis of symmetry. If similar appearance occurs twice in one complete revolution, that is after every 180 degree, the axis is called two-fold axis of symmetry. In case of cubic crystal systems, 6 two-fold axes can be observed. You can observe in this figure, this axis represents two-fold axis of symmetry because when a crystal is rotated along this axis at 180 degree, we get similar appearance. Next, let us see about three-fold axis of symmetry. If similar appearance occurs thrice in one complete revolution, that is after every 120 degree, the axis is called three-fold axis of symmetry. In cubic crystal systems, there are four three-fold axes of symmetry. As you can observe in this figure, this axis represents three-fold axis of symmetry because when a crystal is rotated along this axis at 120 degree, we get similar appearance. Now let us discuss about four-fold axis of symmetry. If similar appearance occurs 4 times in one complete revolution, that is after every 90 degree, the axis is called four-fold axis of symmetry. In case of cubic crystal systems, there are 3 such four-fold axis of symmetry. You can observe in this figure, this axis represents four-fold axis of symmetry because when a crystal is rotated along this axis at 90 degree, we get similar appearance. Now let us know about six-fold axis of symmetry. If similar appearance occurs 6 times in one complete revolution, that is after every 60 degree, the axis is called six-fold axis of symmetry. Cubic crystal systems do not have any six-fold axis of symmetry. In hexagonal crystal systems, six-fold axis of symmetry can be seen. You can observe this axis represents six-fold axis of symmetry. That is, when a crystal is rotated along this axis at 60 degree, similar appearance occurs. Now let us know about plane of symmetry. Plane of symmetry is an imaginary plane passing through the crystal such that it divides the crystal into two parts in such a way that one part is the mirror image of the other. Rectangular plane of symmetry. Cubic crystal systems have 3 rectangular planes of symmetry as shown below. You can observe in this figure, this plane can be considered along x-axis. It divides this crystal into two equal halves. This plane can be considered along y-axis, which divides the crystal into two equal halves. And this plane can be considered along z-axis, dividing this crystal into two equal halves. Next, let us discuss about diagonal plane of symmetry. Cubic crystal systems have 6 diagonal planes of symmetry as shown. 1, 2, 3, 4, 5 and 6. Now let us know what is center of symmetry. Center of symmetry is an imaginary point within the crystal such that any line passing through this point intersects the opposite faces of the crystal at equal distances. You can visualize the center of symmetry from this figure. This point represents the center of symmetry. This line meets the opposite faces at equal distances. This line also meets the opposite faces at equal distances. This also meets these two opposite faces at equal distances. Therefore, this point can be considered as center of symmetry. Now let us know more about total symmetry elements in cubic crystal lattice. Axis of two-fold symmetry 6, axis of three-fold symmetry 4, axis of four-fold symmetry 3, rectangular planes of symmetry 3, diagonal planes of symmetry 6, center of symmetry 1, total symmetry elements are 23. Now let us discuss about laws of crystallography. First one is law of constancy of interfacial angles. This law states that the angle between the corresponding faces or planes forming the external surface of crystal remains a constant irrespective of how the crystal face is developed. Depending upon the conditions under which a crystal is grown, the face of crystal may develop differently, may even appear irregular. The faces of crystal of the same substance may have variable sizes and shapes. However, the interfacial angle is always found to be same. For instance, in all sodium chloride crystals, the interfacial angles remain 90 degrees, whatever may be the size and shape of the crystals. Next law is law of rational indices. This law states that the intercepts of the planes of the various faces of a crystal are small integral multiples of the intercepts made by the unit plane. This law can also be stated as it is possible to choose along the three coordinate axes unit distances A, B, C not necessarily of the same length, such that the ratio of the three intercepts of any plane in the crystal is given by LA is to MB is to NC, where L, M and N are either integral whole number including infinity or fractions of whole numbers. This law is also known as the law of rational intercepts. Next law is law of constancy of symmetry. This law states that all crystals of the same substance possess the same symmetry elements. For example, a cubic crystal always possesses 23 symmetry elements. Now let us know what are Weiss indices. Weiss indices are the coefficients of the intercepts of a given plane on the crystallographic axis. The intercepts made by any crystal plane are usually expressed in terms of the intercepts of the unit plane as follows, that is as LA, MB and NC. Let us try to understand this with the help of this figure. Here ABC plane indicated by rose color represents unit plane. A, B and C are the intercepts made by plane A, B and C. Next, if we take any plane EFG, the intercepts made by this plane are L, this distance is L, this is M and this is N. These L, M and N values can be expressed in terms of A, B and C. So, Weiss indices are nothing but L, M and N values. For unit plane, L, M and N are unity. Therefore, the intercepts made by unit plane are expressed as 1A, 1B, 1C or simply A, B, C. Next we shall see what are Miller indices. Miller indices are the reciprocals of the coefficients of the intercepts of a given plane on the crystallographic axis expressed as integers. Or in simple terms, Miller indices are the reciprocals of Weiss indices expressed as integers. If the Weiss indices of any crystal plane are expressed as LA, MB, NC, then the Miller indices of the plane are represented as HKL, where H is equal to 1 by L, K is equal to 1 by M and L is equal to 1 by N, which are converted to integers by multiplying with LCM. Now let us discuss some of the examples related to Miller indices. How to calculate Miller indices for a unit plane. The intercepts made by the unit plane are A, B, C. The coefficients of these intercepts are 1, 1, 1. That is, Weiss indices are 1, 1, 1. The reciprocals of 1, 1, 1 are again 1, 1, 1. Hence, the unit plane is always represented as 1, 1, 1. We have to make a note here that for a unit plane, both Weiss indices and Miller indices are 1, 1, 1. If the intercepts made by the plane are 2A, 2B and 3C, how to calculate the Miller indices? The intercepts made by the given plane are written as 2A, 2B and 3C. The coefficients of these intercepts are 2, 2, 3. That is, Weiss indices are 2, 2, 3. The reciprocals of 2, 2, 3 are 1 by 2, 1 by 2 and 1 by 3. Now the LCM is taken for 2 and 3, which is equal to 6. Multiplying these reciprocals by 6, we are going to get 3, 3, 2. Hence, the Miller indices for this plane is 3, 3, 2. That is, the values of HKL are 3, 3, 2. Next, if some of the faces does not cut some axis at all, the intercept on this axis is taken as infinity. For example, suppose a face makes intercepts 2A and 3B on the x-axis and y-axis respectively and does not cut the z-axis at all. Then intercepts will be 2A, 2B and infinity. The reciprocals of the coefficients are 1 by 2, 1 by 3 and 0. Here 1 by infinity is taken as 0. LCM of 2 and 3 is 6. Now multiplying the reciprocals of these coefficients by 6, the Miller indices will be 3, 2, 0. If a face makes intercepts on the x-axis and does not cut the y-axis and z-axis at all, then intercepts will be 1a, infinity and infinity. The reciprocals of the coefficients are written as 1 by 1, 0 and 0. Therefore, the Miller indices will be 1, 0, 0. The various faces of the cube in terms of Miller indices may be represented as 1, 0, 0, 0, 1, 0 and 0, 0, 1. In my next video, I will be discussing about derivation of Bragg's equation, determination of structure of NaCl using extra diffraction and isomorphism. Thanks for watching.